Hello everyone, my name is Tejbir and I am a PhD student at IISER Mohali. First, I would like to thank the organizer for providing me with the opportunity to speak about my research work. In this talk, I will talk about reversibility in geometry. First, I will introduce the notion of reversibility and then I will discuss some of my work to classify reversible element in certain groups of geometric interest. Let G be an arbitrary group. Two element F and G in group G are said to be conjugate in G if F equal to H G H inverse for some H in G. An element G of group G is said to be reversible if G is conjugate to its inverse. Further, a reversible element G of group G is said to be strongly reversible if it is conjugate to its inverse by an involution in G. Involution means element of order at most 2. And from definition, it is clear that every strongly reversible element is reversible, but converse is not generally valid. And note the following fact that an element G belongs to group G is strongly reversible if and only if G can be written as a product of two involution. Now let's see one example. Consider the quaternion group Q8 where I, J, K satisfy this relation. Then conjugacy class of Q8 are these. Every element of Q8 is reversible. To see this, just take conjugating element as equal to J for each G in group Q8. And note that plus minus 1 are only involution in this group Q8. So from this fact, we get that plus minus 1 are the only strongly reversible element in group Q8. Now, for an arbitrary group G, one may ask the following reversibility problem that classify the reversible elements and strongly reversible element of group G. For an excellent exposition, one can see the following book, Reversibility in Dynamics and Group Theory. This book has a good collection of open problem in this topic. And now rest of the talk will be based on my recent work with my supervisor, Dr. Krishna Gurupati. Now, the motivation for this work comes from the following paper by Ian Sort. In this paper, Sort classifies the reversible elements in the isometric group of Euclidean space. And these are two main results from this paper. First theorem say that each element of isometric group of Euclidean space is strongly reversible. And second theorem say that if we consider the group of orientation preserving isometry of Euclidean space, then an element is strongly reversible if and only if it is reversible. Now, a natural problem to ask is this, what will be the corresponding result if we consider isometric group of some other metric spaces? And in our work, I have considered F Hermitian space and discussed reversibility in their isometric group. Let's note some terminology before stating our main results. Let F equal to C or H, where C denotes the field of complex number and H denotes the division ring of Hamilton quaternion. Let V equal to Fn and phi be the F Hermitian form given by this equation on V. The Hermitian form phi give a natural metric D on V, and we call V comma D as the Hermitian space. The group of linear transformation G which preserve this Hermitian form phi is called the unitary group over F and denoted by UNF. And this coincides with the standard group of n cross n unitary matrices over F. Now consider the group UNF semi-direct product Fn. This group acts isometrically on Hermitian space V comma D as a affine transformation. An arbitrary element G of this group look like G equal to AB, where A belongs to UNF and B belongs to Fn. Here A is called linear part of G and B is called translation part of G. This affine action identifies the isometric group of Hermitian space V comma D with UNF semi-direct product Fn. And in here we are interested to study reversibility in this group. Following usual notation, we will denote unity group over H by SPN, unity group over C by UN, unitary group, special unitary group over C by SUN. And now we will classify the reversible elements in strongly reversible element in the groups SPN semi-direct product HN, UN semi-direct product CN, and SUN semi-direct product CN. Let's begin with SPN semi-direct product with HN. And first, I want to say that each element of this group is reversible. For strongly reversibility, we have this result that G equal to AV is an element in expansion product Hn, then G is strongly reversible if and only if its linear part A is strongly reversible. Now consider the group UN simulated product Cn. In this group, not every element is reversible. The reversibility depends on the self-duality of the linear part of element in this group, and we have the following result. Note that here reversible if and only if strongly reversible hold, and that further and G is strongly reversible if and only if linear part of G is strongly reversible in UN. And here self-dual mean the characteristic polynomial of an element A in UN is self-dual mean if lambda not equal to plus minus 1 is an eigenvalue, is a root of characteristic polynomial of A, then lambda inverse is also a root of characteristic polynomial of A. And we have this result for reversibility and strong reversibility in UN semi-direct product Cn. The case of SUN semi-direct product Cn is a little more tricky. Here we have equivalence, this equivalence G is strongly reversible if and only if A is strongly reversible. But in case of SUN semi-direct product Cn, this is not whole. In SUN semi-direct product Cn, there are elements which have linear parts strongly reversible, but element itself is not strongly reversible. One example is this. This is one of the examples. And the flow now I will state a theorem. This theorem generalizes the previous example and classify all such elements which are not strongly reversible, although their linear part is strongly reversible. Note this theorem that G belongs to SUN semi-direct product Cn. This is the linear part of G is strongly reversible. Then G is not strongly reversible if and only if up to conjugacy G have this form, that G equal to AV, where A is this and B is this. Here note that minus 1 is not eigenvalue of A. 1 is eigenvalue of A with multiplicity exactly 1, and A have self-dual characteristic polynomial, so it is strongly reversible in SUN. And we also have nice form. It have only one non-zero entry, last entry, and these are the all the elements which have linear part strongly reversible, but corresponding G is not strongly reversible. And this theorem gave us classification of strongly reversible element in SUN semi-direct product Cn, and this is given by this corollary. An element G in SUN semi-direct product Cn is strongly reversible if and only if the linear part of G is strongly reversible in SUN, and G does not belong to the family given in the above theorem. These all results, this talk is based on this paper, and there are some other references. Thank you.